On June the 30th, 1956, two commercial airlines departed LA within minutes of each other, both heading east. One was a United Airlines aircraft carrying 58 people. The other was a TWA Lockheed Super Constellation aircraft carrying 70 people. That morning, both aircraft were flying towards the Midwest. As they approached the Grand Canyon area, weather became a factor. There were thunderstorm clouds nearby, and both crews requested permission to deviate from their assigned course. And individually, these requests were routine, but together they placed both aircraft in the same general region of airspace. And around 10:30 a.m., near the Grand Canyon, the two planes unfortunately collided at 21,000 feet. All 128 people were killed on board. At the time, it was the deadliest aviation accident in US history, and people were shocked. A lot of lives were lost. But also, it was the realization that two large, pretty sophisticated commercial aircraft could just collide in open airspace. The disaster exposed a frightening weakness in aviation. Pilots and controllers were doing their best, but they were working with limited information. Outside normal radar coverage, there was no continuous real-time view of every aircraft. Pilots had to depend heavily on instructions, radio communication, and visual scanning. And as air travel increased, that was no longer enough. Aviation needed something more than human vigilance. It needed an independent system on board the aircraft itself. A system that could detect nearby traffic, predict whether the two aircraft were becoming a threat, and tell the pilots exactly what to do in the final moment of danger. The system is called the Traffic Collision Avoidance System, or TCAS. Really an amazing piece of technology, and more interesting is the code that runs it. The story of TCAS did not begin with just one invention. It began with a problem that aviation could no longer ignore. As commercial air travel grew through the 1950s, 60s, and 70s, the sky became busier. Aircrafts were just flying faster, the routes became more crowded, and the old system still depended heavily on ground controllers, radio communication, and pilots visually scanning the sky. But there was a flaw in that setup. A pilot can only avoid what they know is there. And by the 1970s, aviation authorities were facing a very uncomfortable truth. Air traffic control alone can't be the only safety net. If two aircraft got too close, the warning needed to come from the aircraft itself. One part of collision avoidance is detecting another plane, but the other more important part is coordination. Imagine two aircraft are flying towards each other. One pilot sees the danger and climbs. The other pilot sees the danger as well and also climbs. Now, both aircraft have chosen the same escape path, so the danger hasn't actually gone away. So the real challenge moved from how do we warn the pilots to how do we make sure both aircraft don't make the same avoidance move. And that is what makes TCAS such an interesting system. The aircraft needed more than to just sense each other nearby. They needed to communicate. They needed to compare positions, altitude, and movement. And when that situation became dangerous, they needed the system to issue complementary instructions. One aircraft must climb, but the other must descend. So in 1981, the FAA formally began the TCAS development. And by the late 1980s, the system was being tested successfully, and regulators started moving towards mandatory use on larger aircraft. So aviation was now entering a new era. But introducing TCAS did not mean that the story was over. In fact, one of the most important lessons came after TCAS was introduced. In July 2002, two aircraft were flying over southern Germany. One was a Russian passenger aircraft, and the other one was a DHL cargo aircraft. Both were flying at the same altitude. On the ground, a Swiss air traffic controller noticed the conflict late and instructed the passenger aircraft to descend. But at the same time, TCAS within the aircraft gave the opposite command. It told the aircraft to climb. On the DHL aircraft, TCAS offered the complementary instruction to descend. That meant that the system was working exactly as designed. One aircraft was being told to climb, the other was being told to descend. But the passenger aircraft followed the air traffic controller's instruction instead of TCAS. Now, both aircraft were descending. They collided at 34,000 feet. 71 people were killed. This is known as the Überlingen disaster, and it became one of the clearest and most painful lessons in aviation. TCAS can only protect the aircraft if the pilot trusts it. And after Überlingen, aviation procedures became a lot more clearer. When TCAS issues an advisory, pilots must follow it, even if it contradicts air traffic control. And this is because TCAS knows something very specific. Because TCAS wasn't built to manage the whole sky like air traffic control. TCAS was built just to answer one simple question. If two aircrafts are colliding, what move gives these aircrafts the best chance of surviving? And that's it. At a simple level, TCAS is a system that uses radio signals to find nearby aircraft, measure how close they are, and then predict whether or not they are becoming a threat, and if necessary, tell pilots exactly what to do. But let's break down the tech. The first thing is that there are flying radars. Every TCAS-equipped aircraft is constantly yelling into the ether, "Who's out there?" It does this by sending out interrogation signals on a radio frequency. Any other plane nearby with a transponder will answer. Now, this is basically the same thing that ground radars do, but now it's just plane to plane. Transponders on the aircraft listen for inquiries on a certain frequency and reply with a ping on a different frequency. The ping also includes the identity of the aircraft and the altitude. And then TCAS uses these replies to figure out three key pieces of information about the other aircraft. The first one is obviously the distance. How far away is the other plane? TCAS times how long it takes to get a reply, almost like pinging a server in order to calculate the range. The next piece of information is the altitude difference. We know that the reply includes the aircraft altitude, and TCAS then compares it to its own altitude to see if the plane is above or below and by how many feet. And then lastly, the closure rate. By sending repeated pings, TCAS tracks whether the distance is shrinking and by how fast. Essentially, it tracks the intruder's relative speed and whether it is converging on your aircraft. A fast closure means that you're on a collision course, but a steady distance means no conflict. And combined with the altitude data, TCAS can predict whether the other plane will be at your altitude when you converge. And with all of this, the TCAS computer predicts the future. Specifically, one metric, which is the closest point of approach, known as a CPA. If it looks like, let's say in 30 seconds, you'll be uncomfortably close, TCAS will raise an alert.
Traffic.
It also doesn't wait until the last second. It will use something called time to impact, called TAU or TAU, as a main trigger for advisories. Advisories being the instructions. And depending on how imminent this threat is, TCAS issues two levels of advisories or alerts. One is known as the traffic advisory. This is more of a caution that another aircraft is nearby and it could be a threat. The system will audibly announce traffic. And on the cockpit display, a symbol, often like a yellow dot, will highlight the other plane. So TAs are basically TCAS's version of just saying, heads up, there's a threat nearby. But at this stage, it doesn't tell the pilot to make some sort of maneuver. In fact, with TAAs, pilots are trained not to deviate. You then get resolution advisories, known as RAs. This is when TCAS gets serious. If the closure continues and collision is imminent, often within 15 to 35 seconds depending on altitude, TCAS issues an RA. The computer now decides an evasive action for the pilot. It will command one of the following: climb, or descend, just like that.
Flight directors off.
Increase climb.
There are sometimes other instructions like increase descent or monitor vertical speed, but it is an instruction that the pilot must follow. TCAS is basically taking vertical control to dodge the intruder. And one important part of TCAS is that if both computers have TCAS, their RAs will be coordinated, meaning one plane will be told to go up, the other plane would be told to go down. So this way, they'll always separate vertically. So with that, what exactly is the code that would make TCAS work? So what exactly is TCAS actually doing? Because when I say this is the code that keeps planes from colliding, it sounds like there is one dramatic file somewhere called do-not-crash.c, but there isn't. Now, the actual source code inside certified airline TCAS computers, well, that's not public. That code belongs to the avionics manufacturers, and they obviously want to keep their intellectual property private. But there are many public TCAS-style projects that give us a useful window into how this kind of system is built. An example of this is XTCAS. And this is not certified avionics software, but it is a TCAS 2 version 7.1 implementation, which is designed for flight simulators, not for real aircraft, but it will show the foundation of an actual TCAS computer on board. So let's have a look at the source code. It's written in C. The system is broken into 3 parts. First, there is an acquisition module. So we're on a plane and there is an intruder. The acquisition module is a part that receives air data and any positions from the intruder or any surrounding aircraft. In a real TCAS unit, this data would be supplied by radio interrogation and transponders and other things. In XTCAS, the simulator provides the aircraft positions because it's not a real plane. So once we have the aircraft positions, there is another module known as a TCAS computer module. Now this is the brain. This builds a 3-dimensional picture of the airspace around the aircraft and decides whether to generate traffic advisories or resolution advisories. And then finally, there is the avionics output module. This is a part that will send the results to the cockpit display. Any traffic symbols, alerts, and visual guidelines. So this shows that TCAS is a pipeline. One part collects the aircraft data, another part models the airspace around the aircraft, predicts conflicts, and chooses an advisory, and then the third part communicates that advisory to the pilot. Now, in the XTCAS code, the mode settings are defined by your header file, which you can see here, the 3 basic modes. And this tells us a lot. This here means that TCAS is just not actively protecting you. TA only means that it can only issue traffic advisories. Basically, there's traffic nearby. TA/RA means it can issue both, so traffic advisories and resolution advisories. So now I can also say you need to climb or you need to descend. And the same file defines the threat levels that the TCAS can assign to the traffic. So the code includes categories like this, and this is what you would see on a TCAS display. Other traffic might be shown as a hollow diamond. Proximate traffic becomes more important. Maybe a traffic advisory becomes a yellow symbol, and then a resolution advisory becomes a serious one, a red square. So we know that TCAS has specific modes, and we know that there's specific threats. But how does the system decide which category an aircraft belongs in? This is where the code becomes really interesting, because the system has a structure called CPA, and CPA stands for closest point of approach. This means if both aircraft keep flying as they are right now, what is the closest point that they are going to get? So it doesn't calculate where they are now, it just cares about where they will be when they are closest to each other. And in the source code, the CPA structure stores 3 important things. And if you've done high school physics, this would look familiar. And this is probably a very simplified version of an actual TCAS system in an aircraft. But DT is the time until the closest approach. DH is the horizontal distance at the closest approach. And DV is the vertical distance at the closest approach. So TCAS style logic doesn't really care about how far away is that aircraft. It cares about how many seconds until the closest point, how close will it be horizontally, and how close will it be vertically. And then obviously, are those numbers in a danger zone? Now, the function that creates the CPA, the closest point of approach, is called the make CPA. And inside it, TCAS stores the predicted positions of both aircraft, then calculates the horizontal and vertical separation. Here is a small snippet of the function. I'm not showing every line of the function, but this is the key idea. The system takes the predicted encounter and turns it into 3 numbers: time, horizontal separation, vertical separation. And once you have those 3 numbers, you can start making decisions. So the comments in the TCAS source code actually explain the algorithm in a very clear way. It says that the system constructs a 3-dimensional coordinate space around your aircraft. Your aircraft becomes the center of the world. Then, for each intruder aircraft, it transforms the position into a local space. It then builds a 3D velocity vector for your aircraft and the intruder, and it computes the relative velocity between them. And then the system asks, if I keep moving this way and that aircraft keeps moving that way, where will our paths come closest? Then with that, it's easy to predict when their paths become unsafe. Obviously in aviation, the cost of getting this wrong is enormous. But the code has to be extremely careful about the thresholds, the delays, the vertical speed, and even the type of advisories. You can see that in the TCAS source code. The source code defines a table called RA_, and this table describes the possible resolution advisories. It includes things like any level off advisories, climb, descend advisories, etc. For example, one entry is labeled like this, and another is labeled like that. And this is where the system moves from there's traffic to this is what you should do because there's traffic. The RAs is not a warning like a TA, it is an instruction.
Climb.
And in the same table, each advisory has a sense or a direction of escape. So in code terms, TCAS is one, alerting you that there is another plane, but also offering a set of possible vertical maneuvers. Go upward, go downward, level off. There's other maneuvers also. And each advisory also has vertical speed bands, which is why pilots don't only hear a voice alert. They also see some red and green guidance on the vertical speed indicator. Red means don't fly this vertical speed. Green means this is a vertical speed that satisfies the advisory. Now the code also maps internal advisory messages to human-readable cockpit messages. So for example, you can see here that RA message CLB actually means climb, or RA message DEC means descend, descend. And this is quite a cool detail because the code has to translate geometry and variables into a language that a human can see and obey immediately. So the final phrases that the pilot sees isn't something like vertical separation threshold exceeded. It's something simple. The pilot hears climb, descend, descend, level off, etc. The phrasing matters. Interesting, this is where a bit of TCAS history comes in. In the FAA's TCAS 2 version 2 booklet, there's an update, and they actually say that they have improved the resolution advisories. Before, it used to be something like adjust to vertical speed adjust, and now they've changed it into something more clear where the advisory says level off, level off. And this is such a software lesson because sometimes the bug isn't your algorithm. Sometimes the bug is the command that you give to the human. And if the system knows the correct action, but the pilot misunderstands the instruction, that system can still fail. Before doing my research on it, I thought it was a whole system predicting everything about the aircraft. But it's not trying to understand the entire sky. It is just trying to understand one question. When two aircraft occupy the same sky, will they collide or not? And if the answer is yes, the system only has a few seconds to turn math into a command. Thanks so much for watching. If you like my channel, please like, comment, and subscribe. I'll see you in the next one.